Okay. So can you see the screen as well? Here?
Yes.
Okay. All right. Sounds good. So let me make this full screen. Okay. So last time we were talking about electric fields, right? And we started the discussion for electric field strength. And electric field strength was essentially defined as how much electric force would be exerted per unit positive charge at any point in the electric field was defined as the strength of that electric field. Uh, so the discussion ended with this thing that I was going to show you how does electric field strength varies for any charge as we vary the distance from that charge. Now, inside a charge, or essentially we are going to consider point charges. So there is no such thing as being inside any point charge. It's a point, it's a very small thing, and so there is no such thing as inside that thing. So that means that the electric field strength, inside that would be zero because there is no inside to a charge. Now, as soon as we are at the surface of the charge, in that case, the electric field strength is maximum, right? According to the equation that we're going to talk about, I'll write that equation down in a second. But the electric field strength is maximum at the surface of the charge, and because it follows the electric force also follows the inverse square law, it varies inversely as the square of the distance, so it will be like a curve like this, right? And exactly in the same way it will be a curve in this direction as well, right? And so actually I should draw it. It will not be a positive electric field. It will be in the other direction. So I should draw it in this direction. So it will be something like this, right? So it's zero at the let me fix this. It's very hard for me to draw these lines. So it's going to be zero inside the charge, but it's going to be maximum as soon as you reach the surface of the charge, and then it will start decreasing from there. It's nothing but this law that we studied before as well, that the electric field or the electric force is varies inversely to the square of the distance from the charge, right? So this is how the graph would roughly look like. And so the electric field from any charge, so for example, I'm going to draw a charge over here, and whatever charge this is, suppose it's Q, there will be some electric field around this charge. Now, the bigger the charge is, the stronger the electric field it will generate. So the electric field strength depends on the magnitude of this charge, on the size of this charge. And it depends inversely as the square of the distance from the charge. So if you go 2 meters away from the charge, the electric field strength would drop by 4 units, right? And this helps us to write down an expression for electric field strength, which is the Coulomb's constant K times the charge, which is producing this electric field, divided by the distance squared from the charge. And this is how you can compute the electric field from any that is generated from any charge q. Now I'm going to compare this equation with the equation of gravity, right? So compare this with gravity. We know in gravity, the gravitational field was represented by this G, and it was given as capital G times the mass that was causing this gravity divided by r squared. Now in electricity, the electric field, the field due to electricity is given as the Coulomb's constant K times the charge that is generating this field divided by the square of the distance from this field. There is a very big amount of resemblance between these two equations, except for the fact that you should have remembered is that there will be a negative sign in this expression. While in this expression, there is no negative sign. Now, I want you to tell me, can you take a guess? Why is that so? You just have to remember, I'll give you a hint, just remember the reason for this negative sign. If you remember that reason, then immediately you'll be able to answer why is there no negative sign in this expression. Of course, you should also remember the behavior of like and unlike charges, right? And then compare it. And can anyone answer this thing?
Because gravitational potential energy is zero at infinity, so it's always a negative.
All right, so that could somehow lead to this, yes. But let's for now ignore the potential energy, right? Why was there a negative sign in this thing? Or just recall the expression for force as well, that was minus GMM. I think now it will be much more easier to remember. And the force of electricity is positive K Q1 Q2 divided by R squared. There is no negative sign here, but there is a negative sign here. So think in terms of this force, maybe that would be easier. Why is there a negative sign? Reason for a negative sign. Anyone? Think in terms of the okay, Hasib is also going towards that that work is done against gravity. That will more or less lead to the point that I'm trying to get to, but the main reason is, okay, and a very big hint is due to the nature of the force. Can you take a guess now? The nature of gravity is always attractive to the center of the body that is producing the gravitational field, right? So for example, if this is the gravitational, this object produces the gravitational field, this mass m, then whatever I bring near this mass, it will always be attracted to the center of the capital mass m that is producing the gravity, right? But that's not the case for charges. Charges can be attractive, they can be repulsive, they can behave as both. They're not always attractive, right? So the reason for negative in gravity was because it is always to the center or always attractive. But And so that negative sign was telling us about the direction. It is not outwards, it is inwards. And inwards was associated to that negative signature. And that's why we had that negative sign. In electrostatic force or force due to electricity or charges, you don't see that negative sign because now it entirely depends on the nature of these charges. So what I'm trying to say is, for example, let's say that you have a positive charge Q and another positive charge Q. Then the force on these charges is outwards, right? They're going to repel each other, right? They're going to repel each other, and the force is outwards. Now, outwards is associated to a positive signature. And let's see, what do we get for the force? Force is, so we have plus Q1 and plus Q2. So plus Q1 multiplied by plus Q2, that would remain, let the outside signature be a positive sign, right? So we'll just ignore the sign, divided by R squared. So the value for force F in this case is positive, yani greater than 0. So it's positive. Now, another example could be take a charge, one that is positive and the other one is negative. Then the force is inwards because they are going to snap together. They're going to attract each other. And the force in this case is inwards. Now the force is inwards, right? So let's see, does that give you a negative sign in force? Because if it gives you a negative sign, then it means that yes, indeed, it is inwards. So we have K, one charge is Q1 and the other one is minus Q2. So it would put a negative sign outside and there will be Q2 divided by R squared. So you see, indeed, there is this negative sign, which tells you that this is the case of an inwards, you can say inwards direction, meaning that it's attractive. And that is why we had also, now you can compare it with the equation for gravity. You had this negative sign, and this was telling you that the force is inwards. It was an attractive force, right? So that's the difference between these two forces. That's one of the difference. The other one we saw in yesterday's class, that the force of electricity is a billion times stronger than the force of gravity. In fact, we computed it to be around 10 raised to power 20 times stronger than gravity. So my question now is it clear that is the signature and clear in accordance with the nature of the forces? Right. Okay. Yes. Okay. Perfect. So that's one thing. Right. So now let's try to work out the electric field strength between different types of charges. Right. So I'm going to do that. I think I'll go on the next page. Taking too many pages, but doesn't matter. Okay. So let's try to compute the electric field strength between, let's start with same type of charges, right? So we call it a like charges. So you can take any charges. So for example, if I have two like charges, I'm going to put these charges next to each other. So suppose I have a positive charge over here, and I have another positive charge over here. They're positive charge, so I'm going to see the field lines. I'm just going to draw this field line, right? The field line in the horizontal direction, and they would be outwards from each of the positive. charge. Suppose that this is charge 1 and this is charge 2. So this would be a field line E2 and this would be a field line E1. Okay, so far so good. Now I'm going to pick any point between these two fields or these two charges, and the point suppose lies over here. And now because it's a point, I'm just going to label it P for point. Let's try to compute if I put anything on this point P, what would be the total electric field that the point P would experience, right? Let's compute that. Okay, so is everyone following along what I'm going to do now? Is it is the scenario clear? Right, okay, perfect. Okay, so I'm going to compute the electric field strength, total electric field strength due to two like charges at any point between these two charges, point P. And that's very simple because if you know your directions and the appropriate signature with those directions, then this problem is very simple. Because the electric field strength at point P would be the sum of the electric fields of these individual charges. Because electric field is a vector quantity, and we know that vectors add to each other, right? They behave as a superposition of each other. Now, what that means is that this should be E1, right, plus E1, and then I should add the other electric field to this to get an overall electric field at point P. But remember your directions, right? So E1, if now, how do you think about directions? You should think about your directions by saying that you're sitting on this point P. You would, from one, if you observe the electric fields, from this side, it's to the right, and from this side, it's to the left. So you would add the electric fields in a way that this would be plus E1, and because this is the opposite direction, this would be minus E2. Is that clear? Is the electric field strength the equation that I wrote at point P? Does that make sense to everyone? Okay, perfect. So now it's just a matter of writing these electric fields explicitly. So I know that E1, let me write them separately and then I'll combine. So E1, what should be E1? It's coming from a positive charge. So it will be plus, or we'll just ignore the sign, right? It would be Q1, right? Divided by R squared. Now it's coming from a positive charge. So it's in this direction, it's outwards. So there is a positive sign with this. So the electric field created by the positive charge is positive. And what about electric field strength from charge 2? It would be K Q2 divided by R squared. Again, positive because coming from a positive charge. Now let's put them into this equation. So we have E1 as KQ1 by R squared, KQ1 by R squared. And then you have minus. Now there is something that you should notice about E2, right? When I wrote it as this thing, KQ2 by R squared, right, E2, at that point, I'm just saying that my point P is at some center. But that's a special case, right? That's a special case. I do not want the equation for some specific case. I want a general equation for electric field strength. So what I'm going to do is I'm going to say that this entire axis is my x-axis, right? And if I want to pick a location for point P, I'll just subtract from x, from any point on the x-axis, I'll subtract that location. So it would be x minus r. So whenever I want any value for where my point P lies on this axis, I can just do x minus r, and then I can pick that particular point P, right? So think about this. It makes sense because suppose that if you want your point P to be at the center, then x would be 0. And this means that in place of this r squared for the second, this one, you'll just put x minus r. And the reason for this negative sign is because it could have been x plus r as well. But it's x minus r because I'm choosing that for the second charge. I'm choosing this expression x minus r for the second charge, which is to the right of point P. So if it's to the right of point P, from basic mathematics, the coordinate geometry, we know that if you have to shift, if you shift your origin to the right, then you have to subtract from the axis some number, right? The number that you have shifted. So if this is your, I'll quickly recall coordinate geometry. So if this is the origin, and suppose that I am shifting my origin to some point over here. So this is point 1. I shift my origin here, and I want to say that now this is my origin. So to keep things intact, we say that I'll just subtract from my axis the value that I have shifted it to the right. So I'll subtract 1. So that's exactly what we did over here by doing x minus r. If I had shifted it to the left, then you would add that 1. So if I were shifting my origin to the 1 on this side, then you would say x plus 1. So I assume that you should know this from mathematics, coordinate geometry. But there are some students in the class as well who are not taking mathematics. So that's why I'm trying to explain what I mean by this shifting. And so if I shift to the left, then I plus add that value to the axis, right? And that's why we have this thing as x minus r. So I could have done the exact same thing for E1, but then E1 is to the left of point P. So I would have to add x plus r, right? So is that clear? Does that make sense to everyone? No, Hasib, it's not opposite, right? Because think about this, to keep the physics same, if I'm shifting my origin at this 1, right, to the right, then if I subtract from x that value of 1, then I come back to the original origin. So my original origin should remain invariant, right? So that's why if I'm shifting it to the right, then I have to subtract 1 from the coordinate axis, right? Because think about this, it's like this. So it's like a line, right? And the line ends at some point and it starts at some point. If I'm shifting it to the right, if I'm shifting the line to the right, then I'll pick this end and I'll shift it. Suppose I'll shift it 1 over here, right? That means if I'm shifting it to the right, I'll have to subtract 1 from the end so that the main origin remains invariant. Is it clear? Okay, perfect. All right, so let me move this over there. Okay, so if I do this thing, if I want, so the only reason that we're doing this thing x minus r or x plus r is so that we are not specially talking about any special case where the point P is at the center. We want a general formula for electric field at point P, where the point P can lie anywhere in between these two charges. The condition is that it should lie in between these two charges, not at the center, anywhere in between. It could be at the center, but it might be here as well. It could be here as well. But so to include for that here as well, I will subtract from X this R. If I'm writing it for a charge that is to the right of point P. If I were writing the same expression for E1, then I would add R to X. So I'll write it for both. For example, if I'm writing it for E2, then this should be X minus R squared. Keeping in mind that E1 is written like this. But if I write E2 as K Q2 by R squared, then E1 will be written as K Q1 divided by X plus R, because the charge is to the left of the point P. So X plus R and square it. So these are two possibilities, but they're exactly the same thing. And the reason that they're exactly the same thing will be clear when you put these two independent equations, and I'll not call them independent, but you put these two, E1 and E2, in this expression, or put this E1 and E2 in this expression for EP, you'll get the same result, right? You can check that yourself. So now putting any of these in EP, I'll write EP down over here now. So EP, these would imply EP is equal to K Q1 by R squared minus K Q2 by X minus R squared. So that is the electric field at point P between the charges that are the same charges, right? So you can say that this is the electric field strength between two same charges. So that's this electric field strength. Now you can compute the same thing for between unlike charges, right? And so that's the next thing that I'll quickly do this time. So we have, by the way, is this clear? Is there any question from anyone? Feel free to ask your questions. So any question from from this thing, electric field strength between two same type of charges? Okay, no question. All right. If there is any question, just let me know. Okay. So now we'll also do electric field. The method would be exactly the same, except some minor changes, right? So this will also revise the previous thing that we did. So we want to compute the electric field strength between two unlike charges. So the keywords are between and unlike, right? So that's what we want to compute now. Okay, it's very simple. We'll follow the same thing. We have a positive charge here, and suppose a negative charge here. The axis, they're placed on this axis. Suppose this is some horizontal x-axis, and now this is some charge Q2. This is some charge Q1, right? Q2 has a negative sign with it for obvious reasons, because it's a negative charge. The electric field lines, if I draw from positive charge, it would be something like this, directly outwards. And for the charge that is going, that is negative, the electric field line will be going inside the charge. And now I'm going to pick any point in between these two charges. Suppose this is my point P. So I'll draw it over here now. This is my point P, and the electric field lines, this is E1 line and this is E2 line. So I'll draw it here now. E1 is into this point P, and E2 is outside the point P. Both of these lines are going in a same direction. So the electric field at point P would be the sum of these two electric fields. And because they're in the same direction, so it would be plus E1 plus E2. Right? And now again, in the same way, E1 would be plus Q1, KQ1 divided by R squared. And E2 will be, because there's a minus sign with the charge, it will be minus KQ2 divided by R squared. Does that make sense? Now, the next step is just to put these things in the value of EP. But am I missing something? Can anyone tell me, am I doing something wrong over here? Yes, exactly, right? So I should include for the this thing, it should be x plus r squared, right? And now I'll put these things back into this equation for EP. And when I do this sum, this becomes k q1 by r squared. And then we have this thing as, now I'll make this x minus r and I'll add up. So this will at upstairs, it will take a positive sign, and this will become kq2 divided by x minus r whole squared. So this would be the electric field strength at point P, and that point P can lie anywhere between the two unlike charges. So so now everything that I've been doing so far, what this means is, suppose I have two charged objects to my left and to my right, and I pick any other charged object and put it between these two objects, right? Put it anywhere between these two objects. The electric field experienced by this new object that I put in between these two charges is given by this equation. So the electric field that the new object would feel, which is placed in between these two, would be this electric field. So any questions so far? Is it clear? Okay, clear. Okay, so we have less than 1 minute remaining. The meeting will end. I think we are going a bit slow. If you think so as well, let me know.